Good morning, geology students. I introduced the Earth's Interior lecture this morning, and I'm kind of coming back. And we left on this slide, I was talking about wave reflection, and basically waves entering boundaries of new media at shallow angle are reflected. Either they can be partially or totally. And this diagram in front of you shows kind of the earthquake focus and the propagation of these waves. And one wave, for instance, may be 100% reflector for total reflection here. Or you can also have a wave that's partially reflected, so it's partially reflected here and then refracted into this lower layer here. So again, you don't have to get 100% total reflection all the time. You can get a combination of them both. So here's a seismic survey that was taken from the eastern Gulf of Mexico. So typically they call this is like a sonogram of the Earth, and it's showing you here. These are sediment layers, and you can kind of make out the different layers here and the actual structure itself. So here you can see coming right through here this large kind of structure that kind of wraps around here, and there looks like here there could be something going along. There could be a fault here, and there looks like the layers are faulted here. So this structure is probably has to do with a change in density. It's probably most likely a salt. They call them a salt diapir. So this is kind of what a geophysicist will look at when they get a seismic profile back from a field test. So this is a geologic map that it looks like John Luchai put together. I don't know when he did this, but this is showing just a different type of rock layers on the surface, and it's showing these black lines represent distinct faults that have occurred in these rock layers. And on this next slide, it's kind of a cross section showing from north. This is from north to south, and this is your elevation, which is basically the depth. And this represents 1 mile here. But what it's showing here, these are all these little black lines represent wells. These are actual wells that have been drilled through these different layers of rock. And you can see here the different colors. The brown represents the glacial materials left by the glaciers. And then we have the different rock types, and these are the geologic age. We have the Silurian. This is most likely the dolomite or limestone. Then you have the Maquoketa shale, which is your next layer, and then you have your Sinope group. You have your St. Peter sandstone, and that's where we get most of our drinking water from. And then you have these other kind of the Prairie du Chien, and then the Cambrian, which is we're going deeper in time. But this black, dark black line represents the fault, and that is the Birch Creek Fault. And you can see that these rock layers have been basically offset or displaced. And remember, we talked about what faults are. You can get compression causing the rock layers to be pushed up, and that would be a reverse fault. And then remember, we talked about you pull apart. If you pull apart or have extension, your rock layers are going to drop down. And this, for instance, this one would be the rock layers obviously are dropping. It looks like this is a section where it looks like they're being pulled apart. This rock layer is dropping down here. These are rock layers. It looks like there's some displacement here. So it looks like this is probably most likely a normal fault in here. So this is kind of showing, this is a hypothetical cross-section through the Earth, and this is what it would look like if the Earth was 100% homogeneous. It would travel straight, it would have a straight path through the Earth. Whoops, sorry. This is an example if we gradually increase the density increase the density with depth. We'd get more curvature of these seismic waves. And then here, for an example, this is the real Earth, and these waves travel, and they're reflected and they're refracted, and some go straight, depending on what type of wave it is. So, and that's a function of the density and the elasticity, the elastic properties of the material. So here's kind of an example showing just of P waves. So if we either create a P wave, or a wave that's generated through an earthquake, this is what we have. We're going to have where some of the waves, basically this would be the path of one of the waves through here, and then as it comes in contact with the core, it'll be refracted, and then it'll come through again out here. And remember, P waves go through what? Both solids and liquids. So that's why we have it go, the waves are actually penetrating through the liquid outer core, and then they're going through the solid inner core, and then the P waves end up through on the other side of the Earth. So there is kind of a symmetrical P wave shadow zone that occurs on both sides of the Earth here. Now, if we look at the S wave, or the shear waves, here's an example of what we get with the shear waves. Obviously, there's going to be a huge S wave shadow zone here because the S waves can't penetrate or move through a liquid. So they just go through a solid. So here's kind of showing you this real situation where we have both the P and S waves. Here it's showing P and S waves. Remember, P waves arrive at the station first, followed by your shear wave, and it's showing here you're getting both combinations of P and S waves. And then here, there's no P or S waves here, and then here we only have the P waves that come through here. And this is kind of showing you kind of a integrated diagram here showing how the P and S waves travel through the Earth. This is kind of another kind of diagram kind of showing you it has the densities that are actually on here. So for instance, here's your P wave. This is right this is at the, I believe, the crust, and it comes through here, and as we're going deeper in depth, your density is increasing, and right here is going to be the upper mantle. Here we're entering into the mantle. So you're at 5.5 grams per cubic centimeter here, and then all of a sudden it looks like we have a density increased as 10 to 12 as we enter the liquid outer core, which is here. Okay, and then your velocity. So your velocity is your velocity is down here. So you have a decrease in velocity because you're entering your density is changing, and then now your velocity is kind of gradually increasing a little bit, and you're increasing your density, and then right when you get to the inner core, you've got a little. It looks like you had a little a little increase in velocity, and then it increases a little bit here around this bend in here. So that would be your P wave. So then if we were to look at the shear wave, you start up here, your velocity increases a little bit, and then it increases a little bit. But then right at the upper mantle boundary, it looks like it increases. And then, but the main thing here to point out is right at the mantle liquid core, outer core boundary, it disappears. So our shear waves disappear, and then it reappears in the solid inner core. So that's just showing you kind of a holistic kind of thing, looking at depth and velocity as well as your density. That's kind of a cool diagram. I like this. So this is another kind of cartoon diagram just showing you mainly your thickness of your crust, your oceanic crust, and showing you your velocity variations here. So briefly, we'll talk about heat within the Earth. And I think I'll stop here because I'm right at 10 minutes. So I'll talk to you guys soon. All right.